Okay, this is our last video on one-dimensional motion, so this is going to wrap up our section. And this is going to focus on finding velocity and position from acceleration information. So before we start, let's recall from our previous videos that if we have the position of an object as a function of time, then from that position we can get the velocity just by taking the time, the derivative with respect to time of the position function. And then from this velocity function we can get the acceleration by taking the time derivative of the velocity function. And note that if we plug in the velocity here, that's equivalent. The acceleration is either the first derivative of the velocity function with respect to time or the second derivative of the position function with respect to time. Right, so that's review. That's sort of how we introduced all of the motion quantities. Position, from position you can get velocity, from velocity you can get acceleration. So now we're going to go the other way. We are going to start with acceleration, and we are going to figure out what the acceleration can tell us about the velocity. So starting with this expression, if I integrate both sides with this, and integrate with dt, so I'm just going to add a dt to both sides and then integrate. So when I do that, this side over here just becomes the velocity, and then this side I'm keeping the same, and then there's a constant value that comes about from this integral. And it turns out that this constant value is essentially related to the initial velocity of the object. This is the velocity at any time t. This is essentially related to the velocity initially that the object had. So this expression, the change in the velocity, is given to us by integrating the acceleration function a dt. So integrating that over the entire time that the object is accelerating, that will give us the change in the velocity. Well, what about if we have the velocity function, right? Time derivative of the position function, well, we're going to do the same thing. We're going to add dt's to both sides and integrate. And so this side over here turns into the position at any time, and you get with that a constant. That constant corresponds to the initial position. And this term we're just keeping there. And so this becomes the displacement of the object is equal to integrating v dt, so over the time interval during which you're interested in analyzing the motion. And so the thing that we want to think about, what do these two relationships mean? And the easiest way to show what these things mean and how we can use them to learn about the motion is by looking at a velocity versus time graph or an acceleration versus time graph. Because the integral essentially corresponds to the area under the curve. So let's look at this example. Here I have an acceleration versus time graph. So I've got 7 seconds of motion here. For the first 3 seconds, the acceleration is plus 3 meters per second squared. And for the last 4 seconds, the acceleration is negative 1 meter per second squared. And so if we look up here, I can figure out the change in the velocity of the object during these first 3 seconds if I just calculate the integral here, which is the area under this curve. So this area, or this integral, is rather straightforward. It's just going to be the area of this rectangle, which the height is 3 meters plus 3 meters per second squared. The width is, or the length is 3 seconds. And so when I calculate the area, I get plus 9 meters per second, and that's delta v, that's the change in the velocity. So that means no matter what velocity I started with, after 3 seconds, we're moving plus 9 meters per second faster. Now, after those 3 seconds, the acceleration changes. So now, what happens during these 4 seconds? Well, again, calculate the area. So this is just a rectangle, height minus 1 meter per second squared, length 4 seconds, or looks like I have it written as 3.5 seconds. So the integral there, the area is minus 3.5 meters per second, and that's our change in the velocity during the second part of the motion. So what's our total change in velocity for this entire 6.5 second trip? Well, increase of 9 meters per second, and then a decrease of 3.5, and so the total change in velocity after these 6.5 seconds is plus 5.5 meters per second. What about a velocity versus time graph? So here I've got a velocity versus time graph. The object starts with an initial velocity of negative 3 meters per second and then accelerates in positive acceleration until reaching plus 3 meters per second velocity. Then the object travels at that constant velocity for 2 seconds. And then the object slows down until it reaches 0 velocity. And so if we want to leverage this expression, that the displacement of the object is equal to the integral of v dt, then we need to calculate the area of all of these regions. So first off, in the first second, what's the area of this region? That's just the area of the triangle, height minus 3 meters per second, width 1 second, and so delta x here is minus 1.5 meters for this first second. What about the next second? Well, it's symmetric here, so you can see that the area here is plus 1.5 meter. So the displacement in the first region, minus 1.5 meter. The displacement in the second region, plus 1.5 meter. So actually, at 2 seconds, we're back to where we started. Now, what happens over the next 2 seconds? Well, we're moving at a constant velocity of 3 meters per second, and so our displacement is plus 6 meters during these 2 seconds. And then we slow down, but we're still moving in the positive direction for this last region. And so that area, 1/2, 3 meters per second times 2 seconds. So plus 3 meters for this region. So minus 1.5, plus 1.5, plus 6, plus 3. The displacement over the entire 6 seconds, we just add up those individual displacements. We get a total displacement after the end of the 6 seconds of plus 9 meters. That is, at the end of this journey, the object is 9 meters, if we said to the right was positive, 9 meters to the right of where they started.